by
This
step,
meeting is being recorded.
walking step by step to imagine, to find the lowest point in the valley. But in adiabatic quantum computing, over the mountain and letting its natural flow to identify the lowest point in the valley. So the concept here is the adiabatic quantum computing harnesses the property of quantum systems or its tendency to settle in the lowest energy state. So here, as you can see, when you have an Hamiltonian, and when you make subtle changes, small changes to this Hamiltonian, you eventually come to a state where the solution of that state is the problem that you are trying to solve. And we'll explore this in detail in the further steps. So the first step in adiabatic quantum computing is problem formulation. So the first step is to express your business problem as a mathematical optimization problem. So this involves defining a cost function, f of x, where the goal is to find the global minimum. As an example, if we look at traveling salesman problem, f of x might represent the total distance of all possible routes, and the x, which is the input to that function, could encode the route configurations that one could probably take. So by structuring the problem in this way, adiabatic quantum computing can systematically explore the landscape of solutions to find the most optimal configuration. And the next step is initialization. So adiabatic quantum computing starts with initial Hamiltonian. So this represents the starting quantum state, which can be designed to have a simple, well-grounded state. So this grounded state is easy to prepare experimentally because it doesn't require complex manipulations. Think of it as setting the system in a relaxed, low energy position as the starting point. So once you set your Hamiltonians, you start with the Hamiltonian evolution. So this is the heart of adiabatic quantum computing, where the system transitions from H initial to H final. And H final here is the final state of the of the optimization that you are trying to solve, which in this case is the shortest path that one could take to travel all those cities in traveling salesman problem. So the requirement here is you need to define your H final in such a way that it could encode the solution for the optimization problem that you're trying to solve. So the evolution of this Hamiltonian is controlled by a scheduler function, which is S of t. T is the time function, which can take a value from t equal to 0 to t equal to 1. This scheduler function can be a linear or a sinusoidal function, but the goal here is to maintain the system in its grounded state throughout the evolution. So this ensures that when H final is reached, by making small changes to H initial, the system naturally settles into the configuration that minimizes the cost function f of x. So once the evolution is complete, we measure the quantum state of the system. So this measurement will reveal the configuration X that corresponds to the lowest energy state of H final, which in turn solves the optimization problem. So in our case, the outcome would be the route with the shortest total distance one should travel to cover all the cities. So when comparing adiabatic quantum computing to classical computation or gate-based quantum computing that we discussed earlier, so in classical computing, we start with trial and error approaches. And adiabatic quantum computing completely avoids this trial and error approach. So making it faster and more efficient for large scale problems. And unlike gate-based quantum computing, which requires precise control of a sequence of gates that needs to be applied, adiabatic quantum computing focuses more on optimization, making it much more simpler to implement. So gate-based quantum computing is universal. It can be applied to most of the problems out there. But adiabatic quantum computing focuses more on problems that that revolves around optimization. So it is particularly suitable for applications in logistics, finance, and other domains where this optimization is crucial. And the next model that I want to discuss today is the measurement-based quantum computing. In measurement-based quantum computing, it's an intruding approach to quantum computing, where unlike in the quantum circuit model, which heavily relies on this gate operations, or when you look at uh, adiabatic quantum computing, which revolves around optimization use cases, measurement-based quantum computing takes an entirely different approach. So in measurement-based quantum computing, computations are driven by measurements taken from an entangled quantum state. So what do you mean by entangled quantum state? It's a state where qubits are connected or interlinked in such a way that a change of state of one qubit will change the state of another qubit that is in this entangled state. So this takes the approach from applying gates into three key steps. First is you create an highly entangled quantum state, which is called the resource state, or which is in this case, a clustered state is first prepared. And then the computation is carried out by measuring this individual qubits within this entangled state of clusters. So the result of this measurement guides the computation through classical feedback. So you can think of it like setting up a chessboard. You arrange all the pieces before you begin playing. And once the game starts, each move, which is measurement in our measurement-based quantum computing, will determine the subsequent steps here. So this unique approach has shown promising applications in machine learning, particularly in areas like dimensionality reduction, clustering, and classification. So from a PCA standpoint, in machine learning, more often than not, one may have to work with data sets with thousands of features. So to build an ML model in such high dimensional space is challenging. And always there is this curse of dimensionality in machine learning. So to make sense of these large data sets, we can leverage PCA with quantum mechanics to extract the most dominant features. So there is a version of PCA which uses measurement-based quantum computing, which is quantum enhanced version of PCA, where quantum operations can speed up the computation of this eigenvalues and eigenvectors of that are the end product of after applying PCA. So if you now let's take a look at some comparisons of the models that we discussed so far. So first, on your left, you can see that the feature computational power, hardware requirements, error handling, suitability, and scalability. So from a quantum circuits perspective, these are general purpose quantum models, and these are universal. That means they can apply, you can apply this quantum circuits to solve most of the problems out there. And their hardware requirements is superconducting or trapped ions. But there is more often than not, you have this issue with quantum circuit models where you have to take care of quantum error corrections, which is a huge hurdle at the moment. And these models are suitable in case where when you work with Shor algorithms or Gruber algorithms or in cryptography in general. So the huge challenge from a quantum circuit model is error correction. And when you move on to adiabatic quantum models, these are best suited for optimization use cases. And these work, their hardware requirement is quantum annealers, which one of the practical implementations of this adiabatic quantum models is D-Wave. It's a company that has this adiabatic quantum computing based quantum chips. Um, these are relatively noise resilient but slow because when you, as we said that when we move from H initial, Hamiltonian initial state to Hamiltonian final, the changes to that state should be slow enough such that the qubits are in their grounded state. They are so when you make such small corrections to move along the Hamiltonian or evolve the Hamiltonian, it can be slow. And these are best suited for optimization problems, as I mentioned, like traveling salesman problem, portfolio optimizations, and so on. And scalability wise, these are limited by the problem's size and coherence time. And when you uh, think about measurement-based models, again, these are universal models and also can work in specific tasks. Their hardware requirement is photonic systems. And these are less sensitive to errors during computation and more in the state preparation. Sorry. So these are suitable for quantum cryptography, communications, or distributed computing. But the limitation on the scalability is defined by the state preparation. So where you have to design the state of clusters and how each of these clusters are entangled, and also how these measurements are initiated. So let's take a look at some practical implementations. So quantum circuit models, IBM Qiskit is an open one of the well adapted open source software development kit for quantum computing, which is backed by quantum circuit model. So using Qiskit, you can do simulations of quantum algorithms. You can leverage the circuits, pulses, and other algorithms that we discussed, like Gruber's algorithm or and also this library has implementations of few machine learning models like TensorFlow models and also random forest models. And yesterday, Google announced its newest quantum chip called Willow. So this Willow chip is based on quantum circuit model, which claims that it is capable of solving random circuit sampling problem in just 5 minutes. That would take the world's fastest supercomputer 10 septillion years, which is like 10 to the power of 25 years. So this was just announced yesterday. So I think moving forward, Google and IBM will be more focused on adapting quantum circuit models for their quantum chips. And there is another company called Riget Computing, which also provides quantum cloud services with superconducting qubit processes. This allows users to actually develop quantum algorithms using Queal programming language. Coming to adiabatic quantum models, this adiabatic quantum models particularly leverage the concept of quantum annealing, which has been implemented in a specialized hardware for solving complex problems. And the D-Wave has developed a quantum annealer that utilizes this adiabatic model to address optimization challenges in logistics, scheduling, and machine learning. And there was this use case where D-Wave Systems was working with Volkswagen to explore the traffic flow optimization using their quantum chips, and the results came out to be pretty good. So in such a way that they were able to divert traffic in such a way that there is no bottlenecks at peak hours. And measurement-based quantum computing, it's mostly theoretical. There is this one company called PSI Quantum, which is developing a large-scale fault-tolerant quantum computer based on photonic qubits. And these photonic qubits are helpful from a perspective where if you want to explore protein structures, which are pretty complex, and photonic qubits could probably be leveraged to solve these hidden protein structures much faster. And they are aiming to integrate this quantum computing into existing semiconductor fabrication processes as well. So with that, I would like to actually end my presentation. Dr. Shilpa, I'll hand it back to you. Before we go, are there any questions?
Yes, I'll ask the participants. If you have any questions, you can type in the chat box so that sir will answer. Any questions from anyone? So thank you so much, sir. Having you here is very honor to us, and whatever the industry-related options you have told, that will be a great, information for the students. We can have a question. How can adiabatic quantum computing be scaled up to solve larger and more complex problems?
So adiabatic quantum computing, in by default, the nature of transition of the Hamiltonian is slow. The changes need to be small enough to move to the final Hamiltonian final state where it encodes the solution for your problems. One of the ways that you can scale is having this qubits processed in a parallel fashion, um, uh, such that there is an intercommunication when you are actually uh, applying this changes, so that when this communication, when you can actually have a state where this communications or changes are parallelized, you can probably scale this adiabatic quantum computing process.
Thank you, sir. How does the choice of quantum gates affect the overall complexity and efficiency of quantum algorithms?
So the choice of quantum gates, uh, when you have a long sequence of operations, there is always there is always this chance of quantum diminishing where the results might not be uh, 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 the quantum the qubit might not hold its state for a longer time. So there are researchers going on, and the newest chip that Google announced yesterday, which is Willow, it can, I think it, if I'm not sure on the number, but it can work with quantum qubits around, which is in 100-ish range. And so even the number of qubits that you work with is also constrained by the chip that you are leveraging. Um, and Willow is the most advanced chip that Google has produced so far. And it is still in the hundreds range of number of qubits that you can operate on. And in terms of applying more number of gates, it is always the case. You have to always balance out whether you are having a very long sequence where the state of the quantum itself is diminishing.
Yes. For optimizing machine learning algorithms, is adiabatic quantum computing is better or in different computing models? Which one will be the better for optimization?
So for optimization, adiabatic quantum computing it can be your go-to model because it is the way it is designed is for optimization use cases. So the question also says like
Yeah,
in adiabatic quantum number of qubits.
number of qubits can be increased in adiabatic model.
So again, the model doesn't have any physical constraint, but the chip on which you are running this quantum computation is constrained by the number of qubits it can work with. So I don't think 1,000 qubit chip is still out there, uh, but yeah, it is limited by the chipset that you're using.
Thank you, sir, for answering all the questions. Sir, do you have any question?
You are asking me, sorry, Shilpa?
Sir, Nabi sir,
Madam.
do you have any questions, sir?
No.
Thank you, sir. So we can wind up the session, right, sir?
Okay. Thank you very much, sir.
Thank you.
Narasimha, sir.
Have a good one.
Thank you very much.
Thank you, sir.
Okay.
Participants, please share the feedback of this session through this link. I will be also posting the link in the WhatsApp groups. Please share the feedback. Thank you. I'll be ending the meeting for today. We'll meet you again tomorrow. Thank you. Have a nice day. Sure, ma'am. I'll provide all the related material in the WhatsApp group.